Let's talk about a third form of the Fourier series. So we've talked about the trigonometric form and the compact trigonometric form. So let's talk about the exponential Fourier series. In the exponential Fourier series, the coefficients are often easier to calculate than in the trigonometric forms. So here we have a sum now going from minus infinity to infinity of dn, and then we use these complex functions, complex exponentials, e to the j n omega 0 t, where we calculate the coefficients in the exponential Fourier series. It's 1 over t0, again, the integral over any t0 interval of x of t e to the minus j n omega 0 t dt. Okay. So, reasonable question here is, you see that we've got an infinite sum of complex functions, but we're only working with a real f of x of t. So how does our Fourier sum give a real x of t? Well, when x of t is real, the dn have to have the positive index dn values and the negative index dn values have to have a certain relationship. In particular, the minus index values, dn of minus n, is equal to the complex conjugate of the positive n values. So we don't actually saves us half the work. We don't have to calculate them for the negative n values. We can show, given this constraint, this is actually easy to prove, by the way, directly from the definition of the dn, that we can write x of t, expanding that summation like this, and I'll write it the sum from n equal 1 to infinity of my minus n terms, e to the jn omega 0 t, and my plus dn terms, all I'm doing here is breaking the summation up into the range from minus infinity to minus 1, then the 0 term, and then 1 to infinity, and then explicitly rewriting the negative coefficients. This is d0 plus the sum from n equal 1 to infinity. Here I've got the sum of two complex conjugates, so that's going to be 2 times the real part of one of the terms, dn jn omega 0 t, and I can write the dn in its complex exponential form, and then we can show that x of t then is d0 sum of n equal 1 to infinity of 2 times magnitude of dn cosine of n omega 0 t plus the angle of dn. Okay. So, in other words, this is an entirely real function, and so this summation of these complex exponentials does lead to an entirely real function. The other thing that you can note here is this looks very similar to our compact Fourier series, and in fact by comparing the two, we see that C0 is equal to D0, and then our Cn coefficients are equal to 2 times the magnitude of our Dn coefficients, and then our phase angles in the compact Fourier series representation is equal to the angle of these complex exponential Fourier series coefficients. We can also show that because of the relationships we have between the Cn and our trigonometric Fourier series coefficients, that dn is related to the trigonometric Fourier series coefficients. It's an minus j bn. Of course, d of minus n, which is the complex conjugate of d of n, would then be 1/2 an plus j bn. Since an is, we also have these relationships. An is dn plus dn d of minus n. That's equal to 2 times the real part of d of n, and then our bn coefficients can also be determined from our dn coefficients. It's minus 2 times the imaginary part of dn. And then let's talk about the exponential spectra. Call our amplitude or magnitude spectra and our phase spectra were a plot of our Cn coefficients, the absolute value of our Cn coefficients, and our phase angles. When you're dealing with the exponential spectra, the amplitude spectra is a plot of the magnitude of our dn coefficients versus n omega 0. But now we do this for both positive and negative values of n, so sometimes this is called a two-sided spectra. And similarly, the phase spectrum is both of these are stem plots of the angle of dn versus n omega 0. If x of t is real, the amplitude spectra will have even symmetry. We're only going to work with real x of t in this course. And the phase spectra would have odd symmetry. So this is directly a consequence of that conjugate relationship between the d of minus n and the d of plus n. So for example, amplitude spectrum might look like this: 0, omega 0, 2 omega 0. Of course, these are all going to be positive values because of the absolute value of d of n. But whatever we have for d of 1, we'll have that same amplitude component at minus omega 0. And similarly, whatever we have for at 2 omega 0, we'll have that same amplitude component at 2 omega 0 because of this even symmetry requirement in the amplitude spectrum. Whereas in the phase spectrum, the phase of the DC component will always be 0, but then again, whatever we have at omega 0 and 2 omega 0, we'll have the negative of that at minus omega 0 and minus 2 omega 0. So an easy check on to see if you've drawn these correctly, or probably drawn these correctly in either MATLAB or Octave, is to look for these symmetries.